Welcome to part B of problem 2-4. So you might recall that in part A, we found the unconditional density of X, which was just given as the sum of a weighted average of the conditional densities, where we weighted each of the conditional densities with the probability that exactly that conditional density would be the one in play. So now we need to find the expected value mean of x. So since we know the density of x, it's not hard to find the mean, because if the mean value exists, then the mean of x is just equal to the integral of x multiplied by its density, right? Where we integrate from minus infinity to infinity, but in this case, since the density is only positive on the positive half axis, then we just integrate from 0 to infinity. So the expected value of x we can just find by using this formula. So the mean of x is given by the integral from 0 to infinity of x multiplied by the density of x, which is this. And let's just write this here. So it's the sum from 1 to 3 of Pn multiplied by lambda n e to the minus lambda n x, then dx. And then we can just notice that this here is actually the density of a exponential distribution with parameter lambda n. So just a couple of reminders here of calculus rules. It is that if we have integrals and sums over some positive or non-negative entities, then we're always allowed to interchange them, in the sense that, so if all of my so if anything that I have inside here are all greater than equal to 0, then the integral of the sum of an of x as such can always be equal to the sum of the integral of an of x, no matter what bounds we have. So this is something that you might not have learned yet, but it's a calculational trick that's quite nice to have, is that you can always interchange sums and integrals as you wish, as long as whatever is inside is non-negative. So we can use that here. And the reason why we want to use that is because we can kind of notice that this thing here, it is the density of an exponential distribution with parameter lambda n, right? And if we can move the integral inside with the x, then if we can move it inside, it would be quite nice, because then we would just have the mean value of a stochastic variable that is distributed as such, and we know the mean value in this case. So let's just try to do the switcheroo. So I take the summation outside. I have n equals 1 to 3. And then inside I have the integral from 0 to infinity x multiplied by Pn lambda n e to the minus lambda n x dx. So the Pn is kind of an annoying factor here, because it's not part of the density function of an exponentially distributed variable. But that's okay, because Pn is a constant. So it has nothing to do with x, so I can take it outside of the integral. Now I cannot take it outside of the sum, because Pn depends on n, right? But I can take it out of the integral, and what I have here is the integral of x multiplied by the density of an exponentially distributed stochastic variable integrated from 0 to infinity. So what this thing is I can recognize it as the mean of something that is exponentially distributed with parameter lambda n. So I can just call it the mean of y, where y is exponentially distributed with parameter lambda n. And from this formula here, we know what the mean of an exponentially distributed random variable is. It is 1 over the parameter in question. So what I have is that the mean of x is given by the weighted average of the mean in each of the conditioned cases, which is 1 over lambda n. So it is Pn over lambda n for summed together for n equals 1 up to 3. So just to be completely sure of what we've written here, this is P1 over lambda 1 plus P2 over lambda 2 plus P3 over lambda 3, right? So this is the expected value of x. And again, we can kind of ask, well, was that a surprise? And the answer again is, well, no, not really. Because, well, there is the probability P1 that the storm will be of strength 1, in which case the expected loss is 1 over lambda 1. There is probability P2 that the storm will be of strength 2, in which case the loss will be expected to be 1 over lambda 2, and so on. So this is just the reinforcement of what we expect intuitively. So mean of x, here you go.